BlackLight Power will be a fuel company, and our goal is to facilitate the ability for people to use this worldwide and promote this as the primary energy source to replace other forms of fuel, namely coal, gas, oil, and other forms, as an affordable, sustainable alternative.
A new energy source is definitely needed. Most of my work happens to be in photovoltaics and wind turbines, solar cells and renewable energy systems. And obviously the BlackLight process, based on the chemistry that's involved, could be a renewable and a continuing kind of power source that could be very economic compared with the renewable alternatives. In the large reactor, what BlackLight calls their 50 kilowatt reactor, we're regularly producing over a megajoule, which is 1,000,000 joules of energy. That's equivalent to having a 40-watt light bulb being on for nearly 7.5 hours. And let me just talk about the components that we use. First of all, we're trying to determine how much energy is actually in the BlackLight powder that they've created. And what we've done is we've placed it into a reactor. Basically, a small amount, 15 or 30 grams of the BlackLight material is placed in this cell, and this reactor actually will be heated up. And the way we'll heat it up is we'll provide electrical energy into this ceramic cartridge heater, and then we'll place the entire device inside this very high accuracy calorimeter. This large reactor is one of the most recent tests we've been running down at Rowan University, where this is filled with between 1 kilogram and 1.5 kilograms of the same BlackLight material. And with this device, inside a same kind of calorimeter, just a bit larger, placed inside a very, very well insulated container, we are also able to get a very high degree of efficiency or coupling where we're able to account for nearly 100% of the energy that we put in and the energy that the calorimeter produces. Okay, the heart of the experiment is actually the collecting of the data, because we need to know what the temperature is of the water that's going into the system and the temperature of the water coming out, because that tells us how much heat is being generated by the system. The control experiments are very important because we just put electricity in and we measure how much heat came out, and hopefully they always equal the same amount of heat as the electricity that we put in. But then when we go and put the BlackLight experiment in place, the only difference is now we have the chemicals in there. So we take it up to the temperature, the chemicals react, and we will see a very high spike as those chemicals react and produce a very large heat burst. What's going to happen is you'll see that once the reaction happens, the ramp rate of this will get very, very, very steep, and it will go very, very high, and then the reaction will quench, and then it'll just gradually start to fall back down. Okay, now you just saw that. Did you just see that? It just immediately starts to transition up, and what's going to happen is the scale here will change very quickly, because now we're pretty much off the chart. So what's happening is in this very few seconds, while the data logger is collecting the wall temperature and the inside cell temperature, what we're seeing is a significant burst of heat that's coming out of the cell. So here's the internal cell temperature, and here's the temperature of the outside wall of that cell. You can still see the outside wall was 500 degrees C as well. And it ramped up there in probably less than half a minute or a minute. And so this peak that you see right here, that all just happened in this very, very short period of time, is when the reaction pervaded through that powder, the nickel powder, and basically used all the hydrogen that was available. So there's a very, very, very tiny amount of hydrogen available within the system. So we've run nearly 4 dozen of these experiments over the last 9 months in the small reactor and in the large reactor, to try to convince ourselves that this is repeatable, that this can be done by just about any research lab that would want to use these materials and run through the same calorimetry experiment, and also to convince ourselves of the accuracy of all of the equipment involved. It produces heat like you would expect a chemical coal combustion, oil combustion, or a nuclear reactor, but if you actually look at the chemistry before and after, there is no significant way that we can tell what chemical reaction occurred. We are continuing to do replications, continuing to document the accuracy of the calorimetry experiments.
Okay, these tests validate and confirm that this is a new source of energy that's working now at commercial levels of power, and this should finally facilitate adoption and engagement by the larger engineering and power engineering community to bring this to market.
I think the significance of the experiment is that we have demonstrated a reproducible heat burst of a very high magnitude, which has no other conventional explanations. So it does portend some type of novel energy source or energy evolution mechanism. And it's of a very large magnitude, which can be regularly produced at a scalable level. If in fact the process that BlackLight's developed could be commercially scaled, this would be a very economic replacement for coal and nuclear power as a potential source of generating significant amounts of energy with very little energy put into creating the primary fuel.
The ability to make 200 times the energy that is required to remove hydrogen from water, even seawater, represents potentially the solution to affordable, sustainable energy.